Motors are everywhere. It would not be an exaggeration to say that not a day has gone by where you haven't used a device that contains a motor. In fact, the device you're watching on has a motor in it that you might not even think about. Some motors are in plain sight that you might be aware of. Ceiling fans, power drills, and electric toothbrushes are some of the first that come to mind, but they show up in places you might not even think about. Cell phones have small motors that create a vibration when a phone receives a notification. Computers have motors to spin the fan blades, keeping the computer cool. Some computers utilize a disk drive that requires a motor to read and save data. While you may be familiar with motors in a blender or even the turntable of a microwave, refrigerators have hidden motors that work to compress refrigerants to keep their fridge cool. Motors work because of two basic electromagnetic concepts, current and magnetic fields. Current is the movement of charged particles that flow from areas of high electric potential to areas of low electric potential. High electric potential is an area where more positively charged particles are, and low electric potential is where more negatively charged particles are. Magnetic fields are the result of movement of charged particles and is an invisible field of force that acts perpendicularly to the moving charges. As current is the movement of charges, it both creates magnetic fields and is acted upon by them. Fields hold the convention of north and south, where the north end of a magnetic dipole, dipole meaning two poles, is positive and the south end is negative. Magnetic fields in a dipole flow from north positive and to the south negative end. These two videos demonstrate the attractive and repulsive forces of dipole magnets. In this case, the magnets attract to each other as the ends are opposite. In this case, the magnets repel as the poles are the same. Motors work on the principles of current and magnetic fields to create motion through forces and torque. Force is the acceleration of mass as defined by Newton's second law, force equals mass times acceleration. Torque is the angular acceleration, or rotational movement created due to force when the force is not directly parallel with the center of mass. AC and DC are different ways current is transmitted. AC, or alternating current, is the current that travels back and forth in a closed circuit in a wave-like motion. DC, or direct current, is current that flows in one conventional direction. DC motors are found in small applications like power tools and household appliances, whereas AC motors are found in larger applications such as electric vehicles. This video models a basic DC motor operation. The blue arrows, labeled as B, that is directed from the north to the south pole of the dipole magnet, shows the magnetic field. The red arrows, labeled with I, are the directions of current and stays consistent during the operation of the motor. The two arrows labeled with FB are the directions of force on the current carrying wire at either ends of the axis of rotation, creating torque and rotational movement as indicated with the red arrows. This video demonstrates a more advanced motor operation. The current carrying wire is called the armature. The ring component attached to the end is the commutator, used to ensure the current stays in the same direction regardless of wire orientation. And the two boxes are the brushes that brush along the commutator and provide the current to the wire from the circuit. The two big magnets that replace the bar magnets are called stators and serve as more uniform and more powerful magnets, creating greater torque and rotational movement. This video demonstrates an additional improvement to the motor design by increasing the number of armatures to create greater torque and greater rotational movement from the previous designs. DC motors resemble this model with some more added complexity. That was the basics of motor methods. Thanks for watching.